Black holes are among the most fascinating objects in the cosmos, so extreme that not even light can escape their gravity. They represent a true frontier of our understanding, drawing scientists with their mystery. In this video, we'll explore black holes from birth to the most speculative ideas about them. A black hole isn't a hole in the everyday sense, but a region of space where gravity is so intense that nothing can escape. Imagine spacetime as a stretched rubber sheet. A black hole is like a bowling ball, crushing that sheet so deep that anything sliding nearby falls in. The event horizon is the invisible boundary of the black hole. Once you cross it, the escape velocity exceeds the speed of light. Inside this boundary lies the singularity, a point, or ring if spinning, where density becomes infinite and our physics breaks down. Visually, a black hole appears as a dark shadow surrounded by a glowing accretion disk. Gas spiraling into the hole heats up and emits X-rays and visible light. Powerful relativistic jets can shoot out from the poles propelled by the black hole's spin and magnetic fields. Although we can't see the black hole itself, we see the hot ring of infalling material and sometimes the bent light around it. Most black holes are born from dying stars. When a very massive star, at least approximately 20 times the sun's mass, runs out of nuclear fuel, its core collapses under gravity. A supernova explosion blows off the outer layers, and if the remaining core is more than about 3 solar masses, no known force can stop it from collapsing further. A black hole is born. A slightly lighter core forms a neutron star instead. Black holes can also grow by swallowing gas or merging with other black holes. In 2019, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected a merger of 2 black holes that created a single approximately 142 solar mass black hole, showing that black holes can collide and form even more massive ones. Black holes, especially spinning ones, have several key regions. In simple terms, picture them like this. Singularity, the hidden core of infinite density. Our equations break down here. Event horizon, the boundary where escape velocity equals the speed of light. Ergosphere, for rotating black holes, an outer region where spacetime is dragged around. Theoretically, one can extract energy from this area. Accretion disk, a pancake of hot gas spiraling in. Friction in the disk heats it to millions of degrees, causing bright X-rays and light. Relativistic jets, narrow beams of particles shot out along the spin axis at nearly light speed. Magnetic fields near a spinning black hole launch these jets, which can extend for hundreds of thousands of light years. Even though black holes trap everything inside their horizon, energy can escape in different ways. The Penrose process shows that in a rotating black hole's ergosphere, particles can extract rotational energy. And Hawking famously showed that quantum effects let black holes emit faint Hawking radiation, behaving like a black body. This radiation implies a black hole has a temperature inversely proportional to its mass. Tiny black holes would be very hot and evaporate quickly, while massive ones are extremely cold and stable for eons. What happens as you approach a black hole? From afar, you'd see extreme effects. First, any object, even light, falling in, would be stretched into a thin line by tidal forces, a process whimsically called spaghettification. Stephen Hawking described an astronaut stretched like spaghetti inside a black hole in a brief history of time, giving the effect its name. For supermassive black holes, the effect also flattens objects like pancakes, releasing bursts of energy when stars venture too close. Another hallmark is time dilation. Gravity near the horizon stretches time. A clock near the hole ticks much slower compared to one far away. To a distant observer, something falling in appears to slow down and fade, never quite crossing the horizon. Inside, time still flows normally for the traveler. Once over the horizon, classical physics says we're doomed to hit the singularity. However, modern theories, quantum gravity, etc., suggest new physics may emerge. For now, we say that what happens beyond the horizon remains one of nature's great mysteries. The centers of most galaxies harbor supermassive black holes, SMBHs, with millions to billions of solar masses. Our Milky Way's own SMBH, Sagittarius A, weighs about 4 million suns. The galaxy M87, imaged by the Event Horizon Telescope, has an even heftier SMBH of approximately 6 to 7 billion solar masses. The record holders are quasars like TON 618, whose central black hole is estimated at approximately 66 billion solar masses. These giants shape their host galaxies. Their jets can blow out huge cavities in intergalactic gas, and their gravity influences star formation. We detect SMBHs not by light, they emit none directly, but by their effects. Orbital motion. Stars orbit too fast around galaxy centers for visible mass, implying a massive, unseen object. Gravitational lensing. Black holes' strong gravity bends and magnifies background light. In the distant universe, lensing by black holes can create multiple images or bright arcs of background galaxies. Accretion radiation, gas swirling into SMBH's heats to extreme temperatures, shining in X-rays. Observatories like Chandra and XMM Newton map this hot glow. And relativistic jets. Radio telescopes see jets spanning hundreds of thousands of light years. The bright radio source Cygnus A is an example. Powered by a distant SMBH, its jets light up the sky. These methods let us see the invisible and build the cosmic web's map. SMBHs in young galaxies also hint that black holes and galaxies grew together early in the universe. If light can't escape a black hole, how do we find them? Scientists use indirect methods. Star orbits. Track stars or gas clouds orbiting an unseen mass. X-ray binaries. Look for X-rays from matter heating up as it falls onto a compact object. Many stellar mass black holes were discovered this way. Cygnus X1 is a famous case. Gravitational waves. Since 2015, LIGO/Virgo has detected space-time ripples from black hole collisions. The first detection proved binary, black holes exist, and dozens more mergers have been seen. Future space-based detectors like LISA will catch even more, including merging SMBHs. Event Horizon Telescope. In 2019, the EHT network captured the first image of a black hole's event horizon. This Earth-sized radio telescope array resolved the dark shadow surrounded by a bright ring. Other telescopes, instruments like Hubble, Chandra, and NuSTAR, keep searching for telltale signs. For example, Hubble looks for microlensing events where a rogue black hole bends starlight as it drifts by. In each case, we rely on Einstein's gravity. It predicts exactly how light and matter behave near black holes. By comparing observations to theory, we confirm black holes are real. Gravitational wave astronomy, in particular, has revolutionized the field. It directly hears merging black holes, adding a new tool to our cosmic toolkit. Black holes are not completely black. In the 1970s, Stephen Hawking showed that quantum effects allow black holes to emit faint Hawking radiation. In simple terms, particle-antiparticle pairs pop into existence near the horizon. One falls in while the other escapes, making it look like the black hole is radiating. This radiation has a thermal, black-body spectrum, with a temperature inversely related to the black hole's mass. Small black holes would be extremely hot, while a supermassive one is nearly cold. Over immense time, Hawking radiation causes a black hole to evaporate. But that idea raises a puzzle. What happens to the information about everything that fell in? Quantum theory insists information can't be destroyed. Yet if a black hole completely evaporates into featureless radiation, seemingly all the details of the original matter are lost. This is the famous black hole information paradox. Physicists are actively debating the resolution. One modern idea is the holographic principle, which suggests that all the information swallowed by a black hole is somehow encoded on its horizon surface like a cosmic hologram. Others propose dramatic scenarios like a quantum firewall at the horizon. As of now, there's no consensus. Solving the information paradox will likely require a true theory of quantum gravity. General relativity admits some exotic solutions besides black holes. White holes are like time-reversed black holes. They spit out matter, but nothing can enter. In theory, if you flip the direction of time in a Schwarzschild solution, you get a white hole. However, no one has observed one, and many physicists suspect they exist only in equations, not reality. Some speculative ideas imagine a white hole as the exit of a wormhole or a baby universe born from a black hole. Wormholes are hypothetical tunnels connecting distant regions of spacetime. Einstein and Rosen first found such bridges in 1935, the Einstein-Rosen bridge. Wormholes could, in principle, link two black holes or far-flung parts of the cosmos. Kip Thorne and others have shown how a wormhole could be threaded with exotic, negative energy matter to stay open. While wormholes capture the imagination, featured in many science fiction stories, no evidence currently exists. They remain an intriguing theoretical possibility that future physics might illuminate. Some scientists and philosophers have toyed with the idea that our own universe might reside inside a black hole in a parent universe, or that each black hole spawns a new baby universe. The notion is that the singularity of a black hole could connect to a big bang elsewhere. While wildly speculative, it highlights how black holes blur the line between astrophysics and cosmology. Roger Penrose has even suggested that a white hole could be the exit of a black hole in another universe. In this view, what falls into a black hole here might emerge somewhere else as a white hole. This raises the metaphor of cosmic rebirth, the idea that death collapse to a singularity, could ironically create new life, a new expanding universe. Black holes challenge our intuition, and sometimes scientists do explore these philosophical edges to inspire new ideas or models. Ultimately, black holes force us to confront deep questions. What happens to space and time at extreme densities? Could the inside of a black hole even be another universe? The study of black holes is just heating up. In the coming decades, new tools and theories promise breakthroughs. LISA, Laser Interferometer Space Antenna, a space-based gravitational wave detector planned for the 2030s. LISA will detect waves from mergers of supermassive black holes and even extreme mass ratio inspirals, small objects spiraling into big black holes. Einstein Telescope Cosmic Explorer, next-generation ground interferometers being designed in Europe and the United States. They will see gravitational waves with far greater sensitivity, probing earlier epochs of the universe and rarer black hole systems. Space telescopes. Missions like the James Webb, future X-ray observatories will study the environments of black holes in unprecedented detail, tracing how they affect galaxy formation. On the theoretical side, advances in loop quantum gravity, string theory, and numerical relativity, huge computer simulations, aim to merge Einstein's relativity with quantum mechanics. Black holes, with their extreme gravity and quantum features, are key testing grounds. By studying black holes through observations and theory, we edge closer to a theory of everything that describes our universe.